Today's focus will be on heating and cooling curves. First off, energy is defined as the ability to do work or change anything. Okay, so today's focus will be on 3 different types of energy, which will be phase energy. Phase energy is the energy stored due to the arrangement of particles. So how are they arranged? Basically, what is phase energy? It is the energy that is associated with a given substance due to what state of matter it's in. So whether it's a solid, a liquid, or a gas. Thermal energy is the energy stored by moving particles. Thermal energy is based off of temperature. Okay, so if we change our temperature, we change its thermal energy. Remember, the higher the temperature, the faster the particles are moving. The lower temperature, the slower the particles are moving. And chemical energy is the energy stored in chemical bonds. So in order to change your chemical energy, you need to make something different. Today's focus will really be emphasizing phase energy and thermal energy. We will not really be changing what we're made out of. We're going to be focusing primarily on, well, actually entirely on if it was the same exact compound throughout the entire situation. So if it starts at ice and ends up as water vapor, it is still H2O, so therefore its chemical energy has not changed. So we're really not going to be emphasizing this one today. All right, so which picture shows that gas particles have higher temperatures, and how do you know? So we've got to look at figure A versus figure B. If you look at figure B, you can assume that they are going faster. Why? Because their whooshies are longer, okay? And we're assuming that each whooshie is for an amount of distance over the same amount of time, okay? And so this one means that it's going faster, and therefore it has a higher temperature because faster equals higher temp. All right, key. What happens when we heat up a substance? So let's say we start with ice and we put it on a hot plate. Basically, a hot plate is a small little oven that's exposed to the outside. Really bad drawing, but it's a hot plate. Basically, it's just like a flat stove. Okay, but a heating curve is a graph that shows how temperature changes over time. Okay, so what we did is that we had this ice, we put a thermometer in it. Okay, we made the ice with the thermometer in it. It's now in a glass beaker. Okay, and then we started heating the substance up, and we took its temperature, let's say every 30 seconds, and we recorded it. Okay, and what's interesting is that the shapes of the graphs that are developed are extremely similar regardless of what is being heated up. Okay, now some slopes may be steeper, some flat lines may be shorter, some may be longer, whatever, but the shape, the general shape is the same. And so let's look at that shape. This is the shape that you get when you are heating it up. And I will talk about this part in a little bit. But what first happens is if you were looking at this, and this is the graph that you developed, what you would notice at this point, this part was when it was pure solid. So you would look at this and you would be observing you would be making observations while you were heating this substance up. And we're going to just pretend it's ice. Okay, and we would see solid, so it would be all ice the entire time. And then what we would notice is that at this point in time, right here, we would notice that we would start seeing some liquid, which means what would be going on if I still had ice, which is solid, and some liquid? Well, that would mean that this would be melting. Okay? And then I would notice it would take some time and all of it would melt. And then all of a sudden, I would notice that everything was melted, meaning all of the solid was gone, and I was left with my liquid. And you would literally see this. Which means what is melting? Melting is solid going to a liquid. Okay? And then I would notice I would start seeing some bubbles right around here. And what does bubbles mean? Bubbles means that you're producing a gas. So I would be boiling right now, which is a liquid going to a gas. And if I allowed for the system to be or boil all the way, I would notice that during this time, it would be all a gas. Okay? So here's the key takeaways. All right, and I'm gonna label it a little bit differently. I'm gonna do solid, liquid, gas, and then I'm gonna write down solid going to liquid and liquid going to gas. All right, so the key takeaways. What do you notice happens while everything is the same state of matter? So solid, or a liquid, or a gas. What I hope you notice is that that is the only time that you can experience a temperature change. Triangle means change, by the way. So a change in temperature. Notice that I can change my temperature then, and I can change my temperature when I'm all a gas. Okay? And also note that I only have one state of matter, solid, a liquid, or a gas. Okay? So what is happening during this time? I have my particles speeding up. They're moving faster. Particles are moving faster. How do I know? Because I'm starting from a lower temperature and I'm going to a higher temperature. And I know that as you go from a lower temperature to a higher temperature, your particles go faster. So this one, our particles are moving faster too. And then this one, I know that particles are moving faster. So what's really, really interesting that people don't understand or don't know is that while something is boiling, which is this guy, and while something is melting, what do you notice about the temperature? There is no temperature change. Notice that. So think about it. While I'm boiling water, it is the exact same temperature as soon as I see that first bubble and when I see my final bubble. It is the exact same temperature. It does not get hotter by being on the stove longer. It just converts more of that liquid into a gas. It is the exact same temperature. Same thing with melting. So while I have some stuff that's melting, so let's say a pond outside and it's actively melting after the winter, I am actually not experiencing any temperature change. It will be at 0 degrees Celsius the entire time until all of it is melted. Okay, so there's no temperature change. Now, I do want you to note that there are two key temperatures for water, and this only goes for water. Other substances have different melting and boiling points, as you should note. For water, this guy is 0, and this guy is at 100. And when I talk about 100, I am talking about degrees Celsius. So it's at 0 and 100. And in fact, that's where we get Celsius from. They based it off of the boiling point and the melting, or the boiling point and the freezing point, or the boiling point and the melting point of water. And they said, hey, we'll make melting 0 and we'll make boiling 100. And that's where they actually got those numbers from. Okay, so what is changing? Because something's changing. Because everybody's like, well, I'm heating it up. Well, you're adding heat to the substance, but your temperature change is not changing during these phase changes. So I am experiencing a phase change during this time. So what does that mean? So I'm adding heat and I'm changing my phase, no temperature change, but the heat is all going towards that phase change. Well, let's think about it a little bit. Okay, if you think about liquid going to a gas, if I think about my liquid and I go to my gas, which one has more energy? Well, as you note in previous times, we've stated that liquid has less energy than gas. So by going from a liquid to a gas, we are gaining energy. Okay, so we're actually gaining energy from here to here. It takes more energy to be a gas than it does as a liquid. So therefore you have to supply it if you want it to go from that state to gas, right? If you want to go from liquid to gas. All right, so the other thing is that what is changing also during phase changes? Well, yes, you are changing your phases, and the energy is actually going towards attractions or weakening or breaking them. The liquid is more attracted to each other's particles than the gas. The gas has no attraction whatsoever towards each other's particles. The liquid does. And what I always think of is like if I had an atom or a molecule, I'd say, and then another molecule. Okay, for a solid, what's happening is that it's a really tight cord. okay? And then what happens when you go to a liquid state? What you're doing is you're stretching that slinky, I guess you would say. You're stretching it more, okay? And then when you finally get to a gas, what happens, and they should be even spread up a lot more, you totally broke your slinky. You broke all of these attractions towards one another, okay? So from in part B to C, this is what you would experience. Your slinky is stretching. And then from C to, or then this would be now D to E, you actually broke your slinky. And that takes energy to break your slinky or to stretch your slinky. And that's what's happening during those times. Now a cooling curve is just the exact opposite. Okay, so you just got to think of the heating curve and then go with the opposite. Well, remember, all states of matter, I'm going to use blue so it's similar, all of these guys have to have the same state of matter. So this would be a solid, liquid, or gas. Now you just have to think about it. What state of matter, solid, liquid, or gas, would have the highest temperature, which would be at point A? Well, that would be your gas. So then this would be your liquid and this would be your solid. Now going down, we have gas to this guy is the transition from gas to a liquid. And then D to E would be the transition from I started as liquid and now I'm going to a solid. Okay? Once again, whenever you are going down in temperature, we are changing temperature. This time we are going down, so we are slowing our particles. Okay, same with when you're a liquid, you are changing your temperature, you're decreasing it, and then you are slowing your particles for this situation when you are cooling, and then your delta T here, we are decreasing, and therefore we are slowing our particles again. All right, so once again, what is happening during this time? Because I'm still adding heat, but the heat is not going towards a temperature change. So once again, no temperature change. No temperature change. Okay, but what is changing? Well, we are changing our states, phase change. We are phase changing. That says not, but it means no temperature change, by the way, the one above it. So phase change, which means we are changing our attractions for one another. Change attractions. Same with this guy down here. Okay, and so let's try to figure out what's happening to these attractions. I'm going to focus on D, the transition from D to E. So what is D? D is primarily a liquid. So I'm going to have my liquid, and I am going to a solid. So what happens is my particles get closer together. So if I draw my slinky, you'll note that what happens is that my attraction gets bigger. They are closer together. All right, so let's label really fast the parts of the graph with solid, liquid, and gas for being heated. So we have this one, it's the lowest, A to B would be your solid, this would be your liquid, and this would be your gas. Let's change the parts of the graph that represent a phase change. Remember, phase change has to have two separate phases there, which would be your flat line. So this would be a phase change, this would be a phase change. In particular, this would be going from a solid to a liquid, and the one at the higher temperature would be your boiling, which would be liquid to a gas. Circle where the kinetic energy, remember that's movement, so is changing. So where is your movement, which is emphasized by your thermal, is changing? Well, that would be where your temperature is changing. So it's anytime your temperature is changing. And now let's label where your potential energy is changing because the particles become less attracted to each other, okay? So what am I talking about here? I am talking about phase changes. So where are my phase changes occurring? On my flat lines. All right, hopefully you have a basic understanding of a heating and cooling curve. Remember, a heating curve during any phase and cooling curve during any phase changes, that's when you're experiencing your flat lines. During any change of temperature, that is when you are all the same state of matter, solid, liquid, or gas. All right, and a heating curve, you're just heating them up, and then a cooling curve, you are cooling the substance down. Have a great evening.